de March 2023, no va a ser el próximo, pero es el primero. Sorry, I'm going to speak the Spanish first. Right, that. Realmente hoy tenemos 3 speakers muy, pero muy buenos, importantes, relevantes, y es el recorrido profesional que tienen. Mis disculpas por la tardanza, realmente el tráfico está hoy bonito alrededor. Entonces, de parte de la Junta, con el 23, pues les agradecemos estar acá. Y sin más preámbulos, vamos a iniciar con Andrea. So, thank you very much for being here, and the colleagues are yours. Okay. Thank you.
And does it advance?
Well, because I think do you want me to listen to
All right. My name is Andrea, and I am a geophysicist and also the CEO of OptiSeis, and we specialize in seismic acquisition. So today I am going to talk to you about EcoSeis, a method to reduce the environmental footprint of acquiring seismic data. I'm going to talk a little bit about shallow seismic, as the example that we're working with is from a shallow play, but it does apply to deeper plays. We're going to talk a bit about high density seismic acquisition and the solutions for lowering the footprint while still maintaining good quality subsurface data, and then go through the EcoSeis project. So when we're trying to image a near target, sometimes we can run into challenges. So does anybody know what this is a picture of? Somebody's very good at interpretation. So when we're trying to image for shallow, if we have our lines far apart, it's very good for deep, but if we want to image shallow, and that is a bird, so we have one very good interpreter here, we need to put the lines a lot closer together. So that's going to increase the surface footprint of the seismic. And in Canada, we're often acquiring seismic where we have trees. So we're cutting more trees, it has a larger environmental impact. And over the years, we have been moving from regular seismic programs, I don't think I have a pointer here, but regular seismic programs where the lines might be larger apart, and we're trying to get much better images, so we're putting the lines closer and closer together. We've been having a lot of problems with this in Canada because some of these surveys, the lines are only 30 meters apart. And that can result in cutting up to 25% of the forest when we're acquiring the seismic. So a group of companies, part of the Canadian Oil Sands Innovation Alliance, put forward this challenge to try to get these high resolution images while reducing the land footprint. I'm going to show you an example of what this looks like in the Canadian forest. So what we see here is a grid of seismic lines cut through different types of forest. And you can see some square well pads here, some existing cut 2D lines and access. And what this ends up doing is fracturing the forest, and you begin to lose habitat for sensitive species. This can also allow more predators to get in, so we're having problems with caribou and wolves. And we need a lot of equipment to cut all these lines, so there's more emissions generated as we acquire these programs. Also, as we cut more trees, that's more decomposition of material, releasing carbon, and it costs a lot of money to go in and repair this. So some of the potential solutions are to make the lines narrower, but we need miniature equipment. So there is a seismic program here and a seismic program here. It's harder to see where the seismic program is here because we've made those lines very narrow, but you do see lines in the snow through there. Another method. Another method is to change the geometry. So instead of cutting that grid of sources, we can go to some alternative geometries. But these are going to require advances in processing to infill these areas of missing data. And that's what where EcoSize comes in. So we take aspects of all those ideas to come up with a complete solution to reduce the environmental footprint. Our goal is to have up to a 50% reduction in land footprint and emissions associated with seismic while maintaining good subsurface data quality. Because there's no point in reducing the environmental footprint if we're getting poor data and we have to go and repeat surveys. Now, we also need to do that safely and efficiently in the field. And if we can reduce costs as well, then we have a winning situation. So the project that we worked on to develop EcoSize started with acquisition design ideas. And then we took the data that was created from that through processing, interpretation, and once we had proved that yes, we do get a good subsurface image, then we moved on to phase 2. And in phase 2, we went through the quantitative analysis. And at that point, if this was successful, we would go on to field operations. I'm happy to say it was successful, and we just acquired a program. But let's jump back to the beginning. So the project started in December of 2020 with the idea of looking at miniature equipment. But one of the challenges with miniature equipment is, one of the benefits of miniature equipment first is this is how we typically acquire data in Canada. And if we cut the lines the way we normally do on this geometry, we're going to cut 8% of the forest. But if we make just the source line smaller, we're going to only 6% of the forest being cut, and that's a 25% reduction in cutting. Now, in order to get equipment down the smaller line, we need smaller drills and we need lighter weight equipment. So one of the challenges when we go to smaller sources is that people often say small charges are very weak. So if I drill a shallow charge and I use less explosives, I'm going to end up with a problem where I have less energy overall and I may even be missing some of the frequencies that I need. The good news is we've tested several different types of these sources, and one of them, although it had lower energy, it did have matching frequencies in the on the low end, if the processing was done correctly. And in some places, we can see how the dominant frequency moves up with smaller charges. We were actually improving the high frequencies. This test was again run in Canada, so we're looking at lots of pictures of snow. It's -30 there right now. We're very happy to be here where it's warm.
You're here.
And what we did is we had a 2D line with the same geophones shown in blue here. We had the regular explosive drilled to 6 meters, and then this clear wave by Orica drilled to only 1 meter. When we first saw this charge, we thought, oh, this might not work. So we went very finely sampled. This is the result. If you look at just the shot record, it appears very weak. But when we take that through data processing, you'll notice we focus in on this area here and here, it actually has really good resolution. But there's a problem with this picture and we make a decision on that. We are looking at here higher sampling. So what we need to do is we need to reprocess this from raw shots, so not just dropping the data, but make sure we mimic how it would be acquired in the field, and compare it with the same sampling as the regular explosive source. And you would expect this to be a poorer quality image, but what's unique about this source is it's directional. So it has a shaper in it that will help more energy go into the surface and increase the number of reflections relative to standard explosives. So this proved the concept that for this source, we could go to those narrow lines. There are several other sources that we tested, some that worked, some that are still experimental. So this is ongoing research. The next step in the project was the geometry side. This is where it's really, really fun. I'm an acquisition geophysicist. We get very excited about different geometries. And we started with a data set that was a perfect grid. So one of our clients a few years ago had gone out and acquired this. And from this data set, we were able to generate a whole range of different geometry options. Some of them sparse, orthogonal, slants, linear geometries, some very unusual geometries as well. Now, what happens if we go to a different geometry? We know that we can get a footprint reduction. This is a different example now. So here we're seeing a 22% reduction. It's going to vary depending on the geometry that we use, but usually it's around about 20 to 25% when we go to the narrower lines. So what if we just go to a single set of lines and we put the sources and receivers on the same line? Sorry, I'm just going to go back to that picture here. In Canada, we call this a megabin. It's also been known as a swath. If the lines are too far apart, you're going to end up with rows of bins with no data. So you're going to have to interpolate across of those zero-fold bins. And that can be difficult because you have a whole row of them. Also, if the lines are too far apart, we can run into problems. So normally we don't go from the orthogonal directly to those straight lines. We make those straight lines a little bit closer together. If we do that, then you can see if we cut these regular width at 2.75 meters, even though we put them closer together, there's a little bit of a footprint reduction. But if we can go to the narrower line, now we're achieving numbers we want. This is at over 40%. However, we're still going to have those stripes in the data. Here we are interpolating across, but we do run into problems because of the linearity of these geometries. So the idea we had was, instead of going with straight lines, what if we added some amplitude, basically wiggling the lines in different patterns? And if we're at the regular width, this is the total area reduction. So this is getting exciting. And if we go to the narrower width, now we're achieving about 50% footprint reduction. So how do we test this in practice? Well, we took our grid, and this was sampled with stations and lines all at 20 meters. So basically a perfect grid. And we created the orthogonal data that they normally use in the area. So traditionally, programs would be acquired here with 50, 60, or 70 meter line intervals. This is a shallow target. We're only about 300 meters deep. But we could also create the straight line. This is a hexagonal, this is a sinusoid, and the last one is the zigzag. Now what's neat about this zigzag is we can exactly match these cut lines. So when you repeat a survey, if you have 4D, you only have to recut 50%. We also we tried to get trace density similar on these three. This design and this design are the exact same trace density. This one's slightly higher because of where stations fall. And then this, we found as we went through that we wanted to explore even higher trace density. So the zigzag and the orthogonal match. We have the same number of sources and receivers, same trace density. How do we compare those? Well, there's a cheap way of doing that and an expensive way. So the cheap way is to decimate the fully sampled data right before migrating it. Then we're going to use the same statics, velocities, and noise attenuation as the fully sampled data. It's very affordable, and if it fails here, we know it failed. But if it passes here, it's only a potential geometry because it has all the benefits of the original statics and velocities. The more expensive method is to go right back to the raw shots and decimate at the beginning of the processing. This will match what we would do in the field. So it represents a true test of the amplitude. And we'll have unique statics and velocities and noise attenuation. This trace density and geometry will affect that in the processing. If it fails here, we've got a failure. And if it passes here, now we have an acceptable geometry. So I'll show you the difference between two of these. Just try here. I'm going to flip back and forth like this. So this is the pseudo decimation and the raw shot decimation. First of all, you'll notice a difference in statics. So when you do this properly, different geometries will have different static solutions. And then you'll also notice when we do this properly from the raw shots, throughout the target zone, the amplitudes are decreasing. This is why it's really important to do the testing properly from the raw shots when you're looking at acquisition tests. Now, I will say that when we ran the 10 geometries through, one of them failed at the pseudo decimation stage. So that gave us good information, and then we were able to take some through to the raw shots. Once we had taken everything through processing, then it was time to start comparing it from an interpretation perspective. So that involved doing some well ties and looking at the correlation, looking at time slices, and then looking at amplitude slices. Here we're starting to look at the geology where we flattened on a horizon, so we can start to see some of the faults through here. And what you'll notice is when you move from time to amplitude, you begin to see more of that acquisition footprint. So quite helpful to look at it from that perspective. And then in 4D analyses, we look at the difference in time between two surveys acquired at different times. Here we had surveys basically acquired at the same time, it's the same data set, and we're looking at the NRMS comparison between the fully sampled data and the decimated geometry. And then we can look at phase and frequency and do the same for some of the deeper time slices. So I'm going to show you some of the results. Here we have the grid geometry, the orthogonal, and just the straight line megabit. Now this does have slightly higher trace density than the orthogonal because of where those stations fall in the lines in the original data set. If we look at the time slice, everything looks very similar. Maybe a little smoother when we go to the linear geometries, but really it wouldn't change your interpretation much. But when we go to the amplitudes, now we can see there's more of an acquisition footprint and maybe a little bit of a fading of some of the events, and things get a little smoother with the linear geometries. But these are acceptable, and these are two geometries that are commonly used in Canada, so we want to try to get close to them. This shows us the NRMS, so the difference between the orthogonal and the grid, or the megabin and the grid. And there's some interesting features to notice. There's a gap in the data because we had a well pad, and the orthogonal is interpolating across that gap better than the megabin. Grays are a better match, and as we go to the colors, we're looking at more and more differences. So let's look at how the hexagonal and the sinusoid compare. These are both very low trace density, so they have half the stations. They're going to be much cheaper to acquire. But does the adding in some amplitude benefit? And both of these have the same trace density. This has a little bit of amplitude with lines close together. This has a lot of amplitude on the lines far apart. Significant footprint reduction. So when we look at the time slices, these are auto-picked, and we begin to see a little bit of failure in the auto-picking, but an interpreter could go through, spend a bit more time and probably correct that. But we're not really seeing much acquisition footprint, and it's a fairly good match to what we see on the megabin. If we look at the amplitude slice, though, now we start to see more acquisition footprint. So keep in mind that these are both very low trace densities, so quite cheap. We see the general geology, but on all three of those, we are seeing more acquisition footprint. And this one, the footprint is starting to come through quite strongly in the north-south direction as well. But we see something interesting when we go to the NRMS and the difference. The megabin has that problem, interpolating across the gap. Adding a bit of amplitude onto the line, even though we've taken out 50% of the traces, we're interpolating better across that gap. And here, when we add even more amplitude to the line, we're improving that interpolation across the gap better. But we're introducing other footprint in here. So this gave us the ideas that rather than doing straight lines, we can go to the wavy zigzag lines, but we need to make sure the lines aren't too far apart, and we need to be careful about the trace density. So the next steps were to increase the trace density. So now we have the same trace density as the orthogonal. And here, if we look at the time slice, it is better on the auto picking. There's very few errors, quite comparable to the orthogonal. And if we look at the amplitudes, we do have footprint. It's different. Like the megabin, this is a bit smoother, but pretty good for the footprint reduction we're getting. And when we look at the interpolation across those gaps, we're actually getting a bit better than the orthogonal in this area. And since then, we've done more tests to put in, like, an example of a pipeline or a lake and looking at how that interpolation works. So not perfect, but it's a pretty good answer for a significant footprint reduction. And here we see all of those data sets with their NRMS compared side by side. And the size of the footprint reduction is going to be related to what width we cut the lines in, as well as what geometry we choose. So that finished our phase one, and at that point we said, yes, we can get a good land footprint reduction. We can do this on pre-stack data. And when we go through and do the calculations, we can also get a potential reduction in GHG emissions. And this is something now that we are tracking in the field to prove, because this is from a desktop study. So now we've gone to the field to acquire real data and verify that. Of course, we have more and more ideas coming out of this. So we took that data set, instead of 10, we've now looked at 21 different geometries. Again, different ideas on the zigzags and sinusoids. We started exploring grids. This would only be an area where we're not cutting trees, and taking all of those through pseudo-decimation, and then the best ones going through the full processing from raw shots. As part of phase two, we've also taken the data sets through a quantitative analysis, and I'm going to show you some results from that. So we'll focus in on a comparison of 4 geometries, the right answer. So this is what we expect in the subsurface. That's 60-meter orthogonal, a sparse orthogonal. So now we've gone from 31 to 24 linear kilometers, and that zigzag that matches the orthogonal. When we look at the time slices, when we move to the sparser orthogonal, we have more failures in the auto picking than on the zigzag, and we start to see more acquisition footprint coming through. It gets very interesting when we start looking at the inversion results. So these are acoustic impedance plots. Reds are lows, blues are highs. And we're trying to compare all of these back to the fully sampled data set. Now you'll see if we look at the orthogonal and the zigzag that they're not an exact match, but they are showing geology. Not perfect, but we have a pretty good match in these areas. And when we go too sparse on the orthogonal with our trace density, now that acquisition footprint is going to be better, and you're not able to see the geology. But overall, pretty good match for the acoustic impedance. And then if we look at the VPBS, now we see some very interesting results. The zigzag is getting a bit closer to the original than either of the orthogonals. Both of these are underestimating the VPBS ratio. And part of this is because when we do the zigzag or the sinusoid or any of those other patterns, we have sources and receivers continuously along the line. So we're going to get a better distribution of near offsets and a different distribution relative to orthogonal of nears versus fars. So with an orthogonal, you're always going to be biased to the fars, so you're going to have very few nears. With these zigzags, you're starting to balance that out. And the density shows very similar results. Again, there isn't a perfect answer, but when we start to look at the results from a geological perspective of the density on the zigzag versus the fully sampled data set, we're seeing a better match in places. So we were very excited about these results. Since then, a more thorough quantitative analysis has been run. This is by QI, and Raul is here today. Unfortunately, he's not going to be talking about this today, but he's available to answer questions. We are going to be presenting this talk, the part that I just did, and then Raul is going to go into more detail on the inversion next week in Barranquilla. So what this is showing is we have the sinusoid with those 80-meter lines. We have the hexagonal pattern with the 40-meter lines. I'm not showing the orthogonal grid, but it's that 60-meter grid you saw. We have the straight line mega bin, and then we have the zigzag that matches the orthogonal. And we're looking at the correlation between these geometries and the original grid for acoustic impedance in blue, VPVS in orange, and density in yellow. And you'll notice that the zigzag is performing very well. Its VPVS is actually the best out of all of them, and its density is very comparable. So more work is going to be done. I wanted to show you one other thing. It's quite interesting. So Raul also took this through and broke it down into each of its angle ranges. So here we have 0 to 10, 8 to 18. And what you'll notice is when you start to get above about 15, 16 degrees, you're seeing more geology and less acquisition footprint. And then we get up into very high angle ranges and you're seeing more acquisition footprint again. I'm going to flip back and forth between this one and the zigzag. And I want you to look at kind of the 0 to 10 and the 0 to 18 range. And you'll notice that there is much less acquisition footprint. You're really just seeing geology in the near angles, and the far is improved as well. This comes back to that better distribution of nears, mids, and fars for the zigzag versus an orthogonal geometry. It also has to do a bit with the interpolation. So here we're looking at KX, KY plots. And if you're familiar with these, when you see spikes outside of the central area, it's going to be harder to interpolate the data. It's much easier to interpolate the data if we can minimize those extraneous spikes. You can see on the zigzag that we can minimize those. So if you're interested in discussing this more, we can certainly show you that for all the different geometries. But we're very excited about the results we're seeing here because the zigzag is performing better in processing and inversion. So I'm not quite done, but I do want to acknowledge all the companies that participated in this. Synovus and Imperial on the small source test, Imperial and Suncor on the small source test. Synovus was the one for the 3D data set. Key Seismic did the processing on all of this. Orica is the one that works with the miniature source Clearwave. They produce it, and QI did the inversion work, and then OptiSize did all the interpretation analysis. So phase 1 was, and phase 2 of the inversion here were a success. We have published these results just this month in the Leading Edge. So if you want to read about this in more detail, we can send you the link to the SEG article. If you're not a member, this will be up on our website within the next week. So we can share the link for that with you. Now the next steps are, after seeing the success of the inversion, we have gone out and acquired a data set where we have a conventional 4D and an eco-size 3D. That means we can compare them as 3D surveys. And there's also a baseline that we can compare them back to. So if you think about carbon capture and sequestration, or SAGD for oil sands in injection, you want to come back and do a repeat survey to see the difference over time. But with eco-size, we believe that we can do that repeat survey, lower footprint, lower trace density, and a bit more affordable. So that's one of the things we're going to be testing and processing. We've done some environmental studies. We have just finished acquiring 2 tests examining 7 different types of geophones, looking at their low and high frequency responses and understanding what type of geophone or sensor or node is best for different types of acquisition, as well as examining several miniature sources. And then we're also going through detailed emissions tracking so that we can show how the eco-size program reduces your emissions when you utilize that. And of course, everything that we test goes through processing, interpretation, and QA. So eco-size is applicable to oil and gas exploration, mineral exploration, and we are beginning to use it for clean tech applications such as geothermal and CCS. And before I end, I want to talk to you about why this project was successful. So it's expensive to do these tests. And when one oil company has a data set, they may acquire it, but they don't necessarily have the time or effort to go through all the processing and inversion tests. So this test was part of a consortium of 5 companies. With the success of the first phase, we were able to raise enough money to go to the field and acquire our very own seismic program, with the sponsorship from the Clean Resource Innovation Network and all of these companies. So our plan is to do the same thing in carbon capture. We're actively working on that in Canada. And we are also interested in putting together consortiums like that with companies in other countries. Because when we share resources, it's much more cost effective to go through all these geophysical tests and get accurate results. So the next steps for EcoSeis is carbon capture monitoring. And I want to end again talking about collaboration. To date, we've done over 80 presentations and publications over the history of the company. Not everybody we work with is listed here, as some companies want to remain anonymous, but they are willing to share their data anonymously so that we can further the geophysical sciences. So if there's any topic on acquisition that you would like to talk about, we are here for the rest of the week and available to meet with you tomorrow, Thursday, or Friday. Thank you very much for your time. Yeah, if anybody has any questions, I'd be happy to take them.
Ok, si tienen preguntas para Andrea, las vamos a hacer ahora. Yo voy a barro con el procesamiento, ya como quieran. Andrea, ready to take it? Yes. Okay.
Great presentation, Andrea. Thank you so much. Can you provide a little more detail on the miniature source that you used, Orica one? I guess I'm curious because I haven't really advertised that. Is it available commercially?
It is commercially available, but at this point in time, it has to be custom ordered. So you would need to plan in advance to get access to them, but they can build them. It's something we're working on with them further to look at deeper imaging. So in Canada, this was tested for a shallow reservoir. We're looking at about 500 meters. We're in the process of acquiring a data set looking down to a target of 1,200 meters. So we will have data to show on that in the next 6 months. There are shot tests that were done on targets down to, I think 2.5 kilometers, and they did see up to 60 hertz on the shot records, but that was a very small test, so we don't have full 2D.
And which size?
The size, I believe it's about like that. It's pretty tiny.
And in grams?
In grams, it's the equivalent of about 57 grams.
Are you kidding?
So there is more work we'll be doing and probably some more studies as we get more data that will be published. And there are ideas that we're working on called dispersed source arrays, where you mix these in with very large deep charges, very sparse. So similar to the fiber size concept where you can sweep a very low frequency sweep, but not very often, and then more often sweep a high frequency sweep, but one that's shorter. So this is research that's ongoing between us and the University of Alberta. But yes, very exciting. There may be larger sizes available in the future. Any other questions?
Yeah, thank you. I'm wondering, which would be the benefits from accounting to acquiring, like the seismic, size, but then apart from the footprint reduction?
Yeah, so the purpose of the project at first was to reduce the environmental footprint. However, we are looking at it also from a cost reduction perspective. So the operations are going to be more efficient because we can use a smaller crew and we can move that crew through the field faster. So that's going to reduce your reporting costs. Initially, we're estimating, at least a 10 to 15% reduction in cost, but there's the potential that can even be higher, 25 to 35%. So if you're interested in exploring that more, I could set up a meeting to discuss it with our operations manager as it depends on the size of your program and the amount of equipment you're moving through, but there are ways to make the acquisition much more efficient.
I get a question.
Okay.
When in Canada, the test or what you were showing us, it's in the Portland or it's in the foothills?
This is in the oil sands.
Okay,
So very far northern Alberta, relatively shallow, but we deal with significant problems in the near surface with quaternary channels and difficult imaging. So some of the tests we did with the miniaturized source, we were going through areas where we had really good data quality and then poorer data quality. And we found that by careful processing, we could recover most of the signal through some of those quaternary channels by ensuring the decon was very accurate.
What about the source depth when they're using the meter as sources?
Yes.
Do you need to optimize them accordingly? Because I guess you need to do the same depth as
We
a regular explosive.
Yeah, we deployed them at 1 meter. So some of the testing we did, we went looked as shallow as 30 centimeters, but that was just shot tests. We didn't have enough to do a whole lot of that. One of the ideas is that maybe you could eventually deploy this like a node where you drill the geophone into a shallow hole. You could possibly deploy these as shallow as like 20 or 30 centimeters. So that'd be very fast, efficient acquisition, as you wouldn't need a full-size drill. But at this point in time, because it's experimental and for safety reasons, we're drilling them into 1 meter. We did test some individual ones at 6 meters. If you put them down at that depth, they have even better data.
In Colombia, because of the surface conditions, I mean, topography and environmental restrictions, social restrictions, it is almost impossible to obtain a regular geometry.
Yes.
And, even trying to have like a base highly dense sampling base project would be almost impossible. So what we try to do is to figure out, to which extent you can reduce the number of shots without hurting your data. And there's been big discussions about the use of compressed sensing and multidimensional interpolation, things like that. How do you envision or conceive like a test project in this environment?
Yes. So there have been restrictions on compressive sensing for quite a few years due to some patents. Those have been settled. And while that has been going on, we have been researching what we call controlled random decimations. So there are a variety of ways of implementing compressive sensing. It does go hand in hand with what interpolation algorithm you're going to use. How you might run one of these tests, we're actually still researching that. So you saw we're doing some grid tests. If geophones are easy to deploy, you could have a very irregular grid of geophones and then a sparse grid of sources. We're also looking at the equosize and taking what we just acquired. Here you see perfect, because this was a perfect grid. What we did in the field, the zigzags were wiggly. If we're trying for an 80-meter line, sometimes it's 60, sometimes it's 100, maybe 100, 120, it's going to vary. So we have a geometry now that has all those irregularities, and we're taking it through our controlled random destination to see how sparse we can go on the sources and still maintain good results in inversion. So I would suggest if you were putting together a project like that, we'd be happy to help to come up with an optimal geometry to start, and then go through the tests in processing, interpretation, and inversion to see where things start to fall apart. Yes. Yeah. Who wants to join a consortium here and get tested?
Right.
All right.
So thank you, Andrea.
Thank you very much.
So our next speaker is Rob. Thank you, Rob, for being here. In Spanish?
I'll go with English.
Okay, okay.
16th century stuff. Very good. So I'm Raul. I'm with Thrust Belt Imaging. You may have heard of us. We've been working in Colombia since 2005. We had a private work with our first clients way back in the day when we were actually young people. And we and now we have an office actually in Bogota, and we're really excited about that. But anyway, so that's I'm not here to talk about the. I'm talking about the what I like my favorite seismic imaging technology. So what I'll talk about first is a little bit of kind of background on seismic imaging, kind of the fundamentals. I actually had the good fortune of okay, so maybe
¿Está PDF?
Is that with this? Okay. Yeah, so last year we had or the APG had a publication, Ambient Structural Styles of Seismic Atlas, and I was asked to contribute to the seismic fundamental, some seismic imaging in folded thrust belts. And so Greg Cameron and I wrote that chapter for the book, and it was a good opportunity for us to think about some of the fundamentals of seismic imaging and how they apply to the Andes and folded thrust belts in general. So we'll talk a bit about that, and I'm going to develop a theme of how the importance of working with structural geologists and the integration of geology and geophysics to optimize seismic imaging as the big #1 theme. And then finally, I'm going to talk a little bit about the artificial intelligence or machine learning that we're trying to use to supplement the human learning with our integration with geology. So in keeping with this theme, oh, I get the point. Seismic imaging in fold belts is really for the tough geoscientists. Seismic data and interpretations, obviously. Seismic data in folded thrust belts are characterized by low data density, high noise content, and high geologic complexity. Sometimes I wonder why we bother. And rough topography and near-surface weathering obscure the subsurface. So it's just basically a big mountain of problems under the mountains. Now, I'll talk a bit about how we deal with those issues and look at seismic migration, the fundamental process that creates the final image for interpretation. The two categories, there are a lot of seismic imaging technologies, but the two main categories that they all fall into is a pre-stack time migration, which is a robust method, but the positioning is approximate and the data are in time. Pre-stack depth migration is more accurate, but it's a more delicate process, and it requires a more accurate velocity model, which is good in some ways because it's a delicate process. Then we can make it part of our interpretation and scenario testing for structural interpretation. And I'll show you an example of that. Collaboration with the structural geologist and understanding the regional geologic setting are essential to imaging success. And the other thing about it, so I can't cover all the topics, of course, that are in a chapter of the book, but we have an opportunity here to show animations and demonstrations of technology, which will be better than static images. So here's a static image of a seismic experiment. We've got the source location. Here's the downgoing wave heading into the subsurface. And we've got some reflections coming off of this deeper red reflector. And at some earlier time, the reflection bounced off of this yellow unit. And this is the energy propagating back up to the surface. And this, I think, is more interesting to watch as a movie. You see we've got a strong reflector off the fault plane. And then we're going to have a nice big reflector coming off of this yellow unit. And it's really flying up in the hanging wall. And now this is the reflector off the red unit of the subsurface. And this is moving up towards the surface. And notice that it gives very low amplitude. By the time it reaches here, we've got our downgoing wave has this very strong amplitude. It was very strong at the surface, and it's much less because of the transmission losses and other factors in the subsurface geometric spreading, etc. So I'll just highlight that wave curve as it's heading to the surface. Now this is our reflected wave, and it's obviously going to arrive, or it is arriving right now, at the surface in the hanging wall, and at some later time out here in the foreland, it will eventually get to the surface. So let's think about this in terms of not waves, but rays, and these are the rays as they represent the energy propagating into the subsurface, and they refract at these interfaces, and then come back up to the source, to the surface. And you can see, obviously, this is because of the lower velocity over on the foreland side, it hasn't traveled as far in the same given time. Now, the big difference between time and depth migration is with depth imaging, we do all this ray tracing in order to calculate the travel times to put the reflection energy into the proper place in the subsurface. With time migration, we approximate these with straight rays. You can imagine a straight ray is going to be a fairly reasonable approximation, and then we average through all of the near surface effects of velocity and seismic anisotropy. And in that way, it is a more robust process because we just kind of ignore all the complexity, average it all in, and see how the image shakes out. But here's the fundamental seismic imaging problem: is we record reflections at the surface, but we don't know where they come from. What we want is the position of the reflectors. So here's what a shot record looks like. And you saw Andrea showed some rough data even on a more gently structured area. And it's definitely a lot of complexity. You've got a lot of noise, surface waves, etc., which we can remove in the processing. Here's after a lot of the noise is attenuated, and we can start to see some of this reflection energy peak out into the shot record. So noise attenuation is a big factor. Perhaps a bigger factor in some of these complex structures settings is the near surface weathering. We have hills here for a reason. These are rocks that are resistant to weathering, and the rocks here are probably more susceptible to weathering, and these are likely a depositional setting for the erosion off of these hills, right? So you'll have this harder rocks on the hillside, more with a higher velocity, and you softer material in the valley, and then it's going to have likely a lower velocity, and there'll be time delays across the low velocity material. So out in the foreland side here, we've got this deep foreland reflector. This reflector further up is weak. As we remove the time delays from these low velocity material out here in the foreland, you can see the shifts upwards because we remove that time delay, and the coherency is improved significantly. So we go back and forth, and we've improved it by removing all this localized small weathering problems in the near surface. And the process is called statics, and we apply these static shifts to remove these time delays. Also, and perhaps more importantly, is the subsurface target and the subthrust target here. It's showing a much better coherency, and just throughout we can see stronger coherency as we correct for these near surface weather problems. So that's great, but still, even when we fix those problems, we're still dealing with this issue. Is that we don't really want these diffraction curves or these basically the reflection energy. What we want is the shape of the reflectors that made these. And the process is called migration. So we can move that reflection energy into its position where it actually makes the shape of the shape of the geologic structure that caused these this diffraction curves and these reflection energies. But the thing of it is that we need to know the velocity. So where we saw the anticline was way too broad and the syncline was all crisscrossing, if we over-migrate the data, we do the opposite, where we've got our energies crisscrossing each other over the anticline, and then the syncline is too broad and kind of low altitude. And then we can just kind of look at what happens if we go velocity too low, velocity too high, and back and forth, and we're trying to find a shape that makes geologic sense. Now, it's not quite fair, right? My co-author did some terrible, terrible things to the seismic amplitudes to make this a consistent looking movie. And in practice, if we have the wrong velocity, that's the advantage of having some delicate nature to our seismic imaging, is if we have the wrong velocity, then the imaging is not going to work out very well. So that has the opportunity to QC the velocities in that way. So here's an example of proper pre-stack time migration, where the amplitudes are stacking up when we have this. This is a low velocity pattern, so the near surface is actually pretty good, and the deep reflectors, our anticline syncline pairing here, are not imaging very well because our velocity is too low. And then, so what we're going to see here, as I'll move you through this, is that we'll see what happens when you go to higher velocity and deeper reflectors going to image, and then lower velocity. And then what we'll do is we'll go ahead and make picks along here. As we make velocity picks, this is a composite image that shows real time the updates as we make those velocity picks. So we've got this low velocity, and then we go to higher velocity, and now it's too high. And then we go back to low, to high, and somewhere in the middle, we've got some pretty good reflectivity, so we can make some velocity picks. As we make those picks, then you can see the composite image gets updated real time based on interpolation of all these different velocity patterns. And showing you in 40 seconds, hours of work, but and trust me, it's not as easy as it looks. But now you can see we've got this anticline syncline pairing here. It's imaged really quite nicely. We could obviously do a little bit more work on this. I like this. This anticlinal feature in here is really sharp and clean, and this is kind of broad and doesn't look, it looks a bit under migrated. So obviously with this velocity panel where this plate pick was made would work really well to optimize the image of this reflector as well. Okay, so then we pick those velocities, and they're RMS average velocities from the surface down to the reflection point. So they don't always necessarily make geologic sense. The velocities don't. We want the image to make geologic sense, but we don't necessarily see the velocities making sense, because they're averaging from the surface down to each reflection point. So here's our anticline syncline pair again. Below the anticline, we've got lower velocities than the rocks around. So, sorry, I should have described a color palette. Here we've got the higher velocities are the warm colors, lower velocities are the cool colors. So we've got low velocity on the surface. And so in the area underneath the anticline, we've got higher velocities in the flanks and a lower velocity over the crests. Under the syncline, we've got even higher velocities still underneath the apex of the nadir of the syncline. And then, so that now we've got this higher velocity here. And this doesn't necessarily make geologic sense, but if we think about what we're averaging here, the cause of this is seismic anisotropy, where we've got a higher velocity in the direction parallel to bedding and a lower velocity in the direction perpendicular to bedding. So then, and then of course that bedding orientation is changing all the way across the line. So now, when we try to image underneath the anticline, the seismic energy is propagating at angles pretty close to normal to bedding. Even throughout, it would be pretty much normal to bedding for all of the different array angles. So that's the seismic energy is going to see the lowest velocity over the apex. So that's why we have this lower velocity here. And over to the right, the energy that images this reflection point is going to be at angles oblique to bedding. So it's going to need a higher average velocity to optimize the imaging. Now that's the time migration where we're using these approximations, these averages. With depth imaging, we want a proper geologic model, and when we need to ray trace through this model to correct for all of the propagation effects. So basically what we're doing is that we have to make an interpretation of the subsurface and then ray trace through this model to get an accurate image of the subsurface. So here is an example of that. We've got this, this is the previous example was from the foothills of the Llanos. This is Canadian foothills. And we've got this example here. We've got a geologically constrained velocity model. In the near surface here, this is the lens through which we image the subsurface. And we've got a pretty low data density here. So these are seismic constraints. These are the pre-stacked image gathers. Offset is increasing away from the line in here, so we can see which reflector matches with which pre-stack event. And these are pretty flat. So the principle here is from near to far offset, where the source receivers are close to each other and the sources are far from each other, then if they all image at the same depth, then our velocity is accurate. If it's curving downwards, so in like a frown shape, then the velocity is too high. And if it's curving upwards in a smile shape, then the velocity is too low. And then, but the thing of it is, this all works great in the middle section where we've got a lot of information and we've got good ray angles. But in the shallow, if we zoom in here, we can see that we've got low data density in the near surface. So we only have a few traces to work with. It's hard to say how flat this event is. So it's hard to say how accurate our velocity in the shallow section is. And this is the lens through which we image the subsurface. So I have an example that shows a model test, basically a fault scenario. We've got two different fault scenarios we're going to test here. This is the fault in question. And basically this fault follows the footwall truncations and goes up to the surface. And then we could see that we're having issues with the imaging below. So then when we could see we've got potentially a fault plane reflector to the left, and we checked with the surface geology, and the fault trace at the surface was to the west or to the left in this case. So we tested that out as a different scenario, and you can see in the background how the imaging is actually changing with this different velocity model. And this is the zone of influence of that velocity model change. Then we'll look at that without the velocity overlay so you can see it a little more clearly. And we're definitely getting much more coherency in the basement reflector and this duplex system in here and all the way up this section before and after in the two fault scenarios. So that's the principle around it, or the process around working with the geology team to come up with different scenarios we can test. And it can be helpful not only in improving seismic image, but also helping to constrain the structural interpretation. And I've got a couple of Colombian data examples. This is an interesting one. This is from the Rio Zulia field that we published a few years ago with Echo Control. And we was the same QC display with the offset increasing outward. Beautiful data, really high signal to noise, relatively speaking, for land data. It's a positive flower structure. Lots of wells in the area. It's a development field. And we did the depth migration using the well depths as an extra QC and calibration on the velocity model. Because we're correcting for the heterogeneity and anisotropy, we expect the seismic reflector depth to match the correlated well top in the well. So that's an important constraint. Another interesting constraint is sonic logs. Now I like sonic logs because we have a certain degree of freedom, shall we say, because it's a bit of a range we could pick. But you can definitely see trends. The trends are pretty clear. Velocity gradients and interfaces. And of course we have these well tops in here that we want to make sure that velocity, cumulative travel time down to here results in the velocity that correlates the depth of the reflector with the well top. And here's another example. This is an improvement in the structural model following improved weathering correction. So this is what young Timothy presented at the APG ICE last year. I'm not going to talk about the weathering correction. Basically, this paper was all about using first arrival tomography velocities and other statics corrections for improved weathering corrections. The thing I want to talk about is when he had once he achieved an improved imaging of the subsurface, then we observed that the velocity model we had wasn't very accurate. Like you can see the reflectors are not matching with the horizon boundaries. Sorry, the reflectors are what they are. If the horizon boundaries for the velocity model didn't match the seismic data. So he did updated the geometry, didn't really change the velocity significantly, but he did change the geometry reasonably well, and to now match the seismic geometry, or the geometry of the seismic reflectors, and it resulted in an improved image. So not only in the syncline, here's before and after, and again I mentioned earlier, synclines are tricky to image. So before and after. Also in the footwall of the thrust, we've got much better reflectivity before and now after. Much stronger, and there's a little bit of leftover velocity pull-up on these reflectors and some crisscrossing events in here, and those are pretty much resolved. It's still a bit of a mess, and there could be some additional complexity in here geologically, and just issues with noise, but we definitely have an improvement with, we have this kind of opportunity to have cascading improvements. We improve the image, improve the velocity model, we're going to improve the image further. And this one, just because I like this example, the same data set, this is pre-sec time migration compared to depth migration. And it's definitely, the pre-sec time migration had a really difficult time imaging the syncline and imaging the footwall. And there's definitely some velocity pull-up here with syncline, and then the footwall had a really difficult time. And so that time was displayed with time, and depth was displayed with depth. Okay, so let's talk about this machine learning thing. You know, that's it was a funny thing when Greg, my co-author and the guy that worked on this data science project, he knows like our concern about these automated methods for creating velocity models, because they're often very unstable. They make a lot of assumptions about the range and data density, et cetera, and they usually break down. So we are firm believers in the human inputs and the collaboration and the geoscience integration, as hopefully I've showed examples of that so far. The thing of it is, if human learning is such an important aspect, perhaps machine learning will also be a good supplement to the human learning. And so he asked this question: can we estimate pre-stack depth migration velocity models using convolutional neural networks, or CNNs? So basically, his dream is you give the convolutional neural network the just shot records, and it looks at the shot records and says, okay, I've seen this before, I know what this looks like, and it can come up with this velocity model out the other side. And you know, it's the mixed results so far, but it really looks like a really promising method, especially in the near surface where we have this difficulty with low data density. And that's what I'll show you in a minute. So the motivation here is that automated methods are unstable in these areas, so we rely on human learning. So his question is, can machine learning supplement the human learning? So the process looks simple on the surface of it. He built these training velocity models, which are kind of funny. You'll see them in a second. And then created these synthetic seismic shots from them, and that helps to train the CNN. So the CNN is developing an understanding of the relationship between shot gathers and the velocity model. And then, okay, well then, will it predict it on data or field data? So here's examples of the training data. So we've got the velocity range. We've got dip ranges, so all these different folds and faults that are randomly generated, and then the fault orientations. And you use the information to build the representative models. And they may not look geologic, like I say, they look kind of funny, but they're representative of different dips and velocities. So then here is the field data example. It's the Canadian foothills tree line we looked at earlier. And here's the model that we built with the interpretation and the structural geology constraints in the near surface. And then here's the pre-stack depth migration. It's a beautiful looking seismic image for sure in a complex area. And these are pretty old high velocity rocks. Even our clastics are in the 4,000 meter per second range. And then the carbonates are in the 55 to 6,000 meter per second range. And so it's quite different from kilometers and velocity ranges, but that's an important thing for the CNN to know, is what type of velocity ranges to expect. So then he's got these training models that I showed you. Here's one example. And like I say, kind of goofy, but and then we give like 5,000 of these things to the CNN, and I'm not going to make you watch all 5,000, but and then it comes up with this predictive model. And so now we have this predictive model, and it looks, in the shallow section, it looks almost geological. It's a bit different from what's up here, and we know this came from a cross-section based on the surface geology. So we have to reconcile what's happening in the different dips and the different features in the near surface but it does look reasonably geological up in the very shallow section. It starts to look a bit weak further down, and it doesn't even try to estimate the basement, which is, fine, it's doing its best. But let's look at the results of the data. I mean, the proof, I won't use the English again. The structural model, the image from the structural model looks pretty good around the edges. And the CNN model resulted in an image that broke down the edges. The basement, because we were careful when we built this model to have a cross-section that resulted in a reasonably flat regional basement, then that's pretty flat and pretty coherent. And this is a bit more broken up and definitely not as flat. So it didn't do very well on those aspects. The interesting thing is if we zoom in on this square here, and again I mentioned earlier that synclines are difficult things to image. So you look at these synclines in here, and we've got the previous model is kind of breaking down. It looks okay, but it definitely looks a bit better with the CNN, the machine learning model. And then if we look at this size of the syncline here, and this dipping imbricate here, it looks a little more coherent on the CNN model, which was a bit of a surprise. I mean, this is my favorite one here. I'm going to point with my finger because it's very important to catch the detail here. I don't know if you can see that or not, but it's a duplex. Of course, I love that because it's a duplex. So anyway, very encouraging results. We're not ready to put this into practice yet, but I just wanted to, just show like this is our philosophy, right? Is that we want to bring as much knowledge to bear as we can, and if the machine learning can supplement that, then that's great. Okay, everyone's favorite slide. We're getting to the end. I'll have one more slide of this. Summary and conclusions. Near surface weathering is a major factor in illuminating the subsurface and requires a variety of tools to correct for near surface effects. Geologic constraints and human learning are required to optimize the seismic imaging. And we're hoping that machine learning, at least right now, shows potential to complement the human learning and provide information that we're lacking in our process. So what next? In geophysics talks, we kind of got at least processing. We can definitely in seismic imaging, we get a bit carried focused on our technology, right? And I'm guilty of that as much as anybody. And as seismic imagers, we must never lose sight of the ultimate goal of interpreting and understanding subsurface geology. Integrating the structural geology into the velocity structure helps with this goal, and it's also important to meet the objectives of the final interpretation. So we must not just the process, we want to actually make an image that's interpretable. And in the case of, and this is what I kind of want to make sure to tie it into the next talk when Raul speaks, is that when the data provides an opportunity for quantitative interpretation, then we take everything we've learned about this weathering and velocities and all that, and then we go back to the beginning and migrate the data again using an amplitude preserving workflow. So we can, once we've established an optimum image, we can go back and make sure that we preserve the amplitudes in an appropriate way and learn from the acquisition and the quantitative interpretation team. And again, I would love my collaboration with the structural geologists while building velocity models, also with acquisition designer and QI analysts to ensure the seismic data meets the needs of the amplitude. Yep. That's it. Thank you very much. Any questions? More importantly, any answers?
¿Preguntas? Puede ser en español, inglés.
Inglés, prefiero.
I have an answer for you.
Oh, very good, very good.
So with that CNN algorithm there, you could probably save days of velocity picking and use that to get your initial velocity model and then refine that as a human.
Yeah. That's the direction Greg's heading with the whole thing. Yeah, that's a great idea. I know we'd ask any other answers, and then we'll go to the questions.
No, very clear.
I was very clear. Everyone understands
Yeah,
perfectly.
everything.
So maybe we should have a quiz. Anybody ready for the quiz?
Thank you, Rob. Great presentation. Now, we're going to go with Raul. You're going to do Spanish or English?
Whatever you prefer.
English.
It's up to you. but yeah, of course.
I I think we probably have seen this presentation. Yeah. Buenas noches, de verdad, gracias a todos por quedarse hasta tan tarde para escucharnos hablar aquí sobre diferentes tecnologías que hemos estado trabajando. Y me toca a mí cerrar un poco con lo que estamos haciendo, el esfuerzo que estamos haciendo en todo lo que relacionamos a interpretación sísmica, más específicamente interpretación cuantitativa. Y específicamente voy a estar hablando hoy sobre métodos de inversión sísmica probabilística, que es donde nosotros estamos viendo que la industria de inversión sísmica se está moviendo hacia esa dirección. Esto es un trabajo en conjunto, lo que les voy a mostrar en realidad es una recopilación de diferentes casos de estudios que hemos hecho tanto en la oficina de Calgary como en la oficina de Copenhague, donde están nuestras oficinas principales, y en la oficina de Australia. Simplemente recogí los casos, algunos de los casos más interesantes que hemos trabajado, que ilustran los diferentes tipos de interpretación que se pueden hacer cuando trabajamos con inversión probabilística. Entonces, vamos a empezar primero hablando un poquito de cómo nos enfrentamos nosotros al problema clásico de una clasificación de fase, utilizando datos sísmicos. ¿Okay? Si ustedes vinieran a nosotros y nos dijeran, ok, Raúl, nosotros queremos utilizar datos sísmicos y queremos obtener a partir de datos sísmicos un mapa de arenas, o un mapa, quiero saber dónde están mis arenas, quiero saber dónde están mis arenas más limpias, mis arenas más sucias, dónde están los carbonatos. La manera como nosotros haríamos eso sería tomar la data sísmica, generalmente antes del apilamiento, ¿okay? Una serie de apilados por ángulo, ángulo cercano, mediano, lejano. Hacemos una inversión ABO, ¿okay? Y a partir de esa inversión obtenemos las propiedades elásticas que reproducen esos datos. ¿Okay? Generalmente puede ser un volumen de impedancia acústica, BPBS y densidad. Ahora, cuando nosotros hacemos este tipo de inversión, resulta que nos enfrentamos con un problema, y es que pueden existir diferentes combinaciones de estos parámetros que producen la misma respuesta sísmica. Entonces, ok, ¿qué hacemos? Bueno, en general, todos los algoritmos de inversión de este tipo incluyen una función objetivo que básicamente elige por nosotros cuál es el modelo óptimo que se supone reproduce los datos sísmicos naturales. Entonces, ok, bueno, conocemos las propiedades elásticas del subsuelo o una versión de las propiedades elásticas que deben existir en el subsuelo y hacemos un segundo paso de inversión en el cual vamos a tomar esas propiedades elásticas y las vamos a convertir en propiedades de roca, en propiedades de yacimiento. Generalmente, eso sería volumen de arcillas, porosidad y saturación de fluidos, que son los parámetros por los que generalmente invertimos. Y nuevamente, el proceso de inversión también sufre del mismo problema de no unicidad en la solución de la inversión. De nuevo, pueden existir diferentes combinaciones de arcillosidad, porosidad y saturación de fluidos que en realidad dan resultan en los mismos valores de impedancia acústica residencial. Pero nuevamente, nuestra inversión, nuestro algoritmo, incluye una función objetivo que elige un modelo por nosotros. De tal manera que una vez que conocemos ese modelo de propiedades de yacimiento, entonces ahora podemos utilizar nuestros cortes de arcillosidad, nuestros cortes de porosidad y la saturación de fluido para entonces separar o identificar las litologías que nos interesan. Eso sería nuestro modelo de fase y en un flujo de trabajo determinístico como ese modelo va a ser uno solo. ¿Okay? Que se supone representa o reproduce los datos sísmicos. Ahora,
¿Qué queremos con la inversión probabilística? ¿O cuál es la diferencia con la inversión probabilística? Bueno, una de las diferencias es que con inversión probabilística podemos ir directamente de los datos sísmicos a los modelos de fase. ¿Okay? No necesitamos hacer este tipo de flujo de trabajo con dos inversiones que en realidad terminan pues, complicando el resultado final. Podemos hacer la inversión en un solo paso y la segunda característica bastante importante es que en una inversión probabilística no solamente vamos a explorar una solución al problema inverso, vamos a explorar múltiples soluciones, tantas como sean posibles, de tal manera de que nuestro resultado final en realidad van a ser volúmenes de probabilidad, ¿okay? Que van a venir de las estadísticas que se obtienen de todas las realizaciones de los modelos que probablemente reproducen los datos sísmicos neutrales. Eso lo puedo ilustrar con algunos ejemplos en un segundo, para tratar de aclarar un poco más esa idea. Aquí simplemente tenemos algunas bullet points con la definición de lo que es la inversión probabilística directa, que es el algoritmo que nosotros utilizamos. DPI es una estimación, un algoritmo de estimación de propiedades de roca o fases en un solo paso. Sigue un marco bayesiano que permite la propagación de incertidumbre y básicamente la solución del problema inverso de ABO, de actitud versus causa, con un problema bayesiano. Y esto lo que permite es agregar información teológica que en la inversión determinística en realidad es muy difícil de incluir en el proceso de inversión. Ahora, esto es bastante importante porque agregar esa información teológica nos va a dar dos fuentes importantes de mejora en nuestra solución. Las dos están relacionadas con resolución, ¿okay? Pero dos tipos diferentes de resolución. En primer lugar, al incluir información teológica en el proceso de inversión, vamos a, en primer lugar, obtener mejor resolución vertical, en el sentido de vamos a poder determinar capas muy delgadas, ¿okay? Y en segundo lugar, incluir información teológica adicional que nos va a permitir separar fases o litologías que puedan tener propiedades elásticas muy similares, pero que difieran en algún otro parámetro geológico. Por ponerles un ejemplo bastante simple, el espesor. Digamos que tenemos dos litologías, esas litologías tienen la misma impedancia acústica, el mismo VPS y la misma densidad, pero resulta que sabemos que una tiende a ser más espesa que la otra. Entonces, conociendo el espesor y dando esa información al algoritmo de inversión sobre qué espesor es más predominante en cada capa, podemos separar fases que elásticamente son idénticas, pero que difieren en alguno de los parámetros geológicos que estamos incluyendo en el proceso. Y otra característica bastante importante de la inversión probabilística es que, debido a que la salida ahora son probabilidades, ahora podemos hacer análisis estadísticos más rigurosos, análisis de incertidumbre, por ejemplo, analizando probabilidades P10, P50 y P90 para básicamente modelar escenarios, ¿okay? De cómo pueden estar estas fases distribuidas en el subsuelo. Ok, un poquito sobre los ingredientes que forman parte de este algoritmo de inversión. El más importante en realidad es lo que llamamos el modelo inicial. ¿Okay? Para construir el modelo inicial vamos a comenzar simplemente con una lista de las fases que esperamos conseguir en el subsuelo, que queremos caracterizar. Vamos a incluir información, como les decía, de la distribución de probabilidades de los espesores de cada fase. ¿Okay? Esa información la podemos buscar en los registros de pozo, simplemente mirando los espesores de cada una de las fases que estamos estudiando. y se determina cuál es el espesor medio de cada fase, cuál es el espesor estándar del espesor de cada fase. Algo importante son estas relaciones de orden, y son importantes porque ellas contienen información sobre la estratigrafía que esperamos conseguir en el subsuelo. Entonces, digamos que tenemos una secuencia de engrosamiento hacia arriba, por ejemplo, el tamaño de grano de la hidrología que estamos estudiando. Entonces, sabemos que vamos a comenzar de repente con unas arenas más sucias en la base y de repente arenas de grano más grueso en el tope. Esa información puede ser incluida en el proceso de la inversión a través de esta matriz, que es lo que nosotros llamamos una matriz de probabilidad de transición. Y básicamente lo que dicen, la información que provee esta matriz es, si yo estoy parado en esta fase, ¿cuál es la probabilidad de que la próxima fase en la columna sea cualquiera de estas otras fases, ¿no? Un ejemplo sencillo puede ser simplemente el ordenamiento que esperamos conseguir en la saturación de fluido. Entonces, nosotros sabemos que las arenas con gas siempre van a estar en el tope, debajo de las arenas con gas podemos conseguir arenas con petróleo, y seguido de la arena con petróleo vamos a conseguir arenas con agua. Pero nunca vamos a de repente conseguir una arena con agua directamente en contacto por debajo con una arena con gas. Eso sería una solución geológicamente sin sentido. Entonces, esta matriz no solamente nos da información sobre qué transiciones o qué transiciones son más comunes, sino que también la podemos utilizar para rechazar transiciones que sabemos que no son geológicamente posibles. Ok, entonces con esa información y el modelo estadístico de física de roca, que básicamente contiene, esta es la parte que contiene las propiedades elásticas de cada una de las fases, o sea, promedios de impedancia acústica, de densidad, así como sus desviaciones estándar para cada una de las fases. Toda esa información es capturada en el modelo estadístico de física de roca. Se pueden incluir otros parámetros, como por ejemplo las longitudes de correlación. ¿Okay? Esto nos va a permitir diferenciar fases que, por ejemplo, tengan, de nuevo, una distribución de impedancia acústica, una distribución similar, pero imagínense que una de ellas, las propiedades varían más rápido que la otra. Entonces, imagínense una arcilla, una lutita, bastante homogénea, comparado con una lutita que puede tener de repente los mismos valores de impedancia acústica o densidad, pero más heterogénea, y que por lo tanto muestra variaciones más rápidas de la propiedad elástica. Entonces, de nuevo, se trata de incluir parámetros adicionales que nos permitan al final tener una mejor caracterización de las fases que queremos separar. Entonces, de manera bien esquemática, ¿cómo funciona todo esto? Bastante sencillo, simplemente vamos a agarrar toda esa información inicial, ¿ok? Y vamos a generar cientos, si no millones, de realizaciones de posibles modelos o secuencias de fase que pueden reproducir los datos sísmicos de entrada. ¿Ok? Eso básicamente es lo que está representado aquí. Luego vamos a tomar nuestros datos sísmicos, vamos a extraer un vínculo, vamos a condicionarlo y vamos a utilizar una vínculo básicamente para localizar el problema. Y esto es algo clave en nuestra propuesta de la inversión probabilística. En algunas otras soluciones, el problema se trata de resolver de manera global. ¿Okay? Lo que estoy tratando de decir es que en otros algoritmos se trata de resolver por la secuencia de fases que reproduce toda esta traza. Eso es un problema bastante complejo y computacionalmente muy costoso. Por esa razón, en algunos de esos casos, ustedes van a ver algoritmos que simplemente producen 50, 100, un número bien limitado de realizaciones. Nosotros, en vez de tratar de resolver el problema completo para la traza, utilizamos la aurícula y intentamos resolver, ok, cuál es la configuración de fases que necesito para reproducir los datos que se encuentran dentro de una ventana, que es aproximadamente del tamaño de la aurícula. Y eso es lo que nos permite hacer cientos, miles de cientos de realizaciones, sino millones en algunos casos. Entonces, el objetivo es calcular esta probabilidad. ¿Cuál es la probabilidad de que alguna fase exista, dado esta input, esta entrada de traza seismica? Entonces, el resultado, luego de integrar los resultados de cada una de estas ventanas, estamos resolviendo el problema, va a ser un par de un segmento, donde cada color es la probabilidad de alguna fase. Cada color es una fase, y el ancho de cada uno de esos colores es la probabilidad de esa fase. Entonces vamos a ilustrar esto con algunos ejemplos usando datos reales. Estos datos son de Australia, solo para darles una idea de lo que se usó para resolver aquí la inversión sísmica. Se utilizaron 8 angle stacks, entre 5 y 40 grados de ángulo de incidencia, y datos de registro de pozos de 8 pozos que se encontraban en el área y 4 horizontes regionales que existían interpretados en esta área. Nosotros hemos hecho proyectos y es uno de los si se quiere, estigmas de la inversión probabilística es que inmediatamente hay que decir, hey, probablemente para esto siempre necesitas un número bastante grande de pozos. No necesariamente es el caso. Nosotros hemos hecho proyectos con hasta 3 pozos solamente. Ciertamente requiere un trato cuidadoso de esas probabilidades iniciales, de ese marco inicial de probabilidades, y de las fases, incluso de las fases que se incluyen en el proceso, porque obviamente con 3 pozos de repente todavía no has creado todas las fases que puedas conseguir. Puede haber una fase que no has perforado todavía y que necesites incluir de todas maneras la solución. Eso es posible hacerlo, aunque no se tengan los datos de pozo disponibles. Ok, entonces, un vistazo aquí a los datos sísmicos para que se utilizaron en este proyecto. A la izquierda, un apilado de ángulos cercanos, a la derecha un apilado de ángulos lejanos. Y la flecha amarilla aquí indica la ventana donde se encuentra el objetivo. El objetivo que se quería perforar en este caso era una lutita, ¿okay?, de baja reflectividad, de tal manera que con esas características, pues su interpretación es bastante difícil. De hecho, o sea, es bastante difícil identificar aquí o aquí algún horizonte continuo que al ojo inmediatamente pudiera ser correlacionado con el objetivo que se quiere identificar. Entonces, estos datos se pusieron a través del flujo de inversión probabilística. Aquí está básicamente la interpretación de fases que se hizo en una localización en uno de los pozos que se utilizaron en el proyecto. El objetivo es esta lutita, este intervalo verde aquí con la etiqueta F. ¿Okay? Ese es el objetivo. Aquí a la derecha tenemos las probabilidades iniciales. Entonces, fíjense, las probabilidades iniciales son bastante suaves, o sea, es nuestro conocimiento general de qué esperamos conseguir. Pueden imaginarse estas probabilidades como, si se quiere, el estado de la información antes de correr la inversión, o sea, básicamente esto es lo que sabemos antes de correr la inversión. Aquí les estoy mostrando cuál es la probabilidad inicial para para el objetivo, para esta lutita, ¿okay? Entonces, nosotros estimamos que esa lutita en realidad se encuentra básicamente en algún lugar de esta ventana, ¿okay? Y este es el resultado luego de la inversión. ¿Okay? Amarillo son valores altos de probabilidad y los grises y los blancos son valores bajos de probabilidad. Entonces, la vista aquí en el perfil de pozo pueden ver cómo la lutita que queríamos conseguir, en efecto, la inversión nos está diciendo con una alta probabilidad que esa lutita se encuentra aquí, en esta profundidad. Si vemos la probabilidad inicial que le habíamos asignado a esa lutita en ese intervalo, pueden ver que la probabilidad inicial es relativamente baja. ¿Ve? Porque en realidad estamos diciendo, bueno, sí, está aquí, pero no estamos seguros. Y al exponer los datos sísmicos a este algoritmo de inversión, la inversión básicamente nos está diciendo, bueno, ¿sabes qué? En realidad existe una alta probabilidad de que esa lutita exista aquí. ¿Okay? Algo importante, el espesor de esta lutita es apenas de repente unos menos de 20 milisegundos. ¿Okay? Es un espesor bastante pequeño en comparación con la resolución sísmica. Mucho más al extremo es esta fase azul. ¿Okay? Estas son arenas cementadas que el operador de esta área quería mapear, quería también identificar. Y fíjense, por ejemplo, en estas arenas cementadas aquí, en azul, de nuevo, teníamos una baja probabilidad inicial, no sabemos en realidad dónde se encuentran esas arenas, y la inversión nos está diciendo que hay una alta probabilidad de que esa arena exista en esta profundidad. Entonces, y fíjense que el espesor de estas fases azules es mucho más pequeño que incluso el espesor de la lutita que estamos tratando de identificar. Ahora, uno puede darle un pequeño twist al problema y en vez de invertir por la probabilidad de que una fase exista en un punto de profundidad, uno puede invertir por la probabilidad de transicionar a una fase. Y esa transición de una fase a otra básicamente define un reflector sísmico, o debería definir un reflector sísmico o una superficie donde existe un cambio de propiedades elásticas. Entonces, hicimos ese pequeño twist en el problema y ahora lo que mostramos aquí en amarillo es la probabilidad de tener una transición hacia una lutita. O sea, nuestro objetivo es la lutita. Entonces, ahora amarillo representa la zona o el intervalo donde existe una probabilidad alta de transicionar hacia la lutita. E incluso la transición es desde y hacia la lutita, entonces podemos identificar en realidad el tope y la base de la lutita. Y este es un ejemplo que a mí me gusta muchísimo porque básicamente esto es interpretación automática de horizontes utilizando datos alveolares. En vez de utilizar un volumen apilado con todos los ángulos, en el cual el algoritmo que hace el tricking automático en realidad solo recibe como entrada un solo dato, una sola amplitud para cada muestra de tiempo. En este caso, nosotros estamos utilizando 8 valores de amplitud para cada valor de tiempo. Y la respuesta ABO para cada muestra de tiempo básicamente nos permite tener una mejor definición de dónde se encuentran las transiciones de una fase a otra. ¿Okay? Entonces vamos a un segundo caso de estudio. De nuevo, en este caso, una aplicación totalmente diferente a los resultados de inversión probabilística. En este caso, el objetivo era construir modelos de P10, P50 y P90 para simulación, ¿okay? Para la simulación de yacimiento. Igualmente, los objetivos principales, por supuesto, incluían mejorar la resolución de los arenas objetivos, los cuales se encontraban por debajo de la resolución sísmica, tener un mejor entendimiento de la saturación de fluidos y proveer una mejor interpretación de una inconformidad que se encontraba en la base de la secuencia y que este método también puede detectar de manera más correcta. En este caso, estamos ahora en Alberta, o sea, estos son datos de la cuenca sedimentaria del oeste canadiense. Y aquí tenemos de nuevo 3 diferentes pozos. ¿Okay? En este caso, el color gris representa una lutita que se encuentra justo por encima de nuestras arenas objetivos. En este caso, las arenas saturadas por petróleo están en rojo, las arenas saturadas por agua están en azul, y el verde aquí abajo en la base representa el carbonato que se encuentra debajo de esa fotografía. Entonces, las probabilidades iniciales, de nuevo bastante suaves, bastante generales, y luego de la inversión obtenemos básicamente una actualización de esa probabilidad con mucho más detalle. Y entonces podemos ver ahora que la inversión nos está tratando de decir, mira, sí, cerca de este tope hay una probabilidad relativamente alta de arenas con hidrocarburos. Este es el espesor, por ejemplo, de la lutita que se encuentra por encima. Y algo importante en este proyecto es que había algunas arenas que eran un objetivo secundario que se encontraban en la parte superior de la sección, y que la inversión también nos está diciendo que existe una probabilidad relativamente alta de que esas arenas existan y por encima del yacimiento primario. Una muestra de los datos de entrada, solo para ilustrar que tampoco necesitamos datos sísmicos perfectos para correr inversión probabilística. Esto es lo típico que vemos en los datos sísmicos terrestres en parte de Canadá. La sección está un poco comprimida para un poquito exagerar todas esas variaciones de amplitudes y los problemas que presentan los datos terrestres en Canadá, pero o sea, lo que queremos ilustrar es que estos procesos funcionan incluso con datos terrestres de relativamente mala calidad. Ahora, si corremos la inversión determinística y tratamos el problema, tratamos de hacer la clasificación utilizando el flujo de trabajo estándar, esto es más o menos lo que vamos a tener. ¿Okay? De nuevo, los verdes aquí son la probabilidad de los carbonatos, el azul representa las arenas con agua, el rojo las arenas con petróleo, el color gris oscuro son las lutitas que se encuentran al tope de nuestras arenas objetivo. Y pueden ver que en realidad la inversión determinística nos da una respuesta decente para los carbonatos. Los carbonatos parecen estar bien localizados y seguir el patrón que esperamos, pero la respuesta o los resultados para las arenas son bastante confusos. O sea, tenemos arenas que aparecen, desaparecen, de repente se convierten en lutitas aquí, vuelve a aparecer la arena con hidrocarburos, pero entonces ahora no está esa lutita gris oscuro que esperamos conseguir, sino que transiciona directamente en otra arena saturada con hidrocarburos. Entonces, los típicos problemas que podemos conseguir cuando trabajamos con inversión determinística para resolver este asunto. La inversión probabilística nos da una sección que luce bastante diferente, pero que sigue las características que esperamos conseguir de acuerdo a la información lógica con la cual configuramos básicamente un problema de inversión. Si voy determinístico, probabilístico, determinístico, probabilístico. Entonces, mucha mejor resolución vertical. ¿Okay? Pueden ver ahora que las arenas con agua siempre están en la base, ¿okay? Inmediatamente sobre los carbonatos, separados por esa desconformidad. Luego tenemos las arenas con hidrocarburos, ¿okay? Y luego tenemos esa lutita gris oscuro, ¿okay? Que básicamente representa el sello del reservorio, y ahora su continuidad lateral es mucho mejor de lo que veíamos antes. Por supuesto, existen zonas donde la solución todavía no es perfecta, pero esto se aproxima mucho más a la geología que esperamos conseguir en esta área. Ok, con esas probabilidades podemos entonces hacer los análisis de 10, de 50, de 90, y básicamente ahora estamos mirando un solo pozo, el pozo número 1, y estamos viendo el modelo P10 para cada una de estas litologías. la lutita gris oscuro, una lutita suave, que se encuentra directamente encima del reservorio. En el modelo P10, esa lutita tiene este espesor. Las arenas con hidrocarburos, en el modelo P10, pues muestran un espesor bastante grande. Este modelo P10 generalmente se asume como el modelo más optimista, pero básicamente es el que nos proporciona mayores espesores de arena con hidrocarburos. Fíjense que en el modelo P10 tenemos una buena detección de las arenas con hidrocarburos por encima de la lutita que separa el reservorio principal del objetivo secundario, y la ubicación del tope del carbonato coincide perfectamente con lo que se encontraba con lo que se había interpretado en el pozo. Modelo P50, modelo promedio, ¿okay? Tenemos ahora menos espesor de arena con hidrocarburos, ¿okay? El tope del carbonato ahora se encuentra un poco más abajo, y el modelo P90, que sería el modelo más pesimista, porque solo nos da las zonas o los intervalos donde estamos estrictamente seguros de que una fase exista, o sea, intervalos donde existen más del 90% de probabilidad de que una fase exista, por lo tanto tienden a ser bastante pesimistas este tipo de modelos. Fíjense que ahora tenemos menos espesor de esta lutita, menos espesor de la arena con hidrocarburos, ya no tenemos las arenas que forman parte del objetivo secundario, y fíjense que incluso este modelo está prediciendo el carbonato a una mayor profundidad. ¿Cuál es la idea de todo esto? Que ahora tenemos diferentes modelos de cómo esas fases pueden estar distribuidas, diferentes modelos de cuáles pueden ser los posibles espesores de cada una de estas fases, y ahora se pueden correr simulaciones y evaluar cuáles de estos escenarios son económicos o no son económicos, y tomar decisiones de perforación utilizando información sísmica. Por último, voy a terminar con algo bastante nuevo. ¿Okay? Yo creo que es, si se quiere, el próximo paso en la evolución de estos algoritmos de inversión probabilística. En este caso, lo que hemos hecho es incluir efectos anisotrópicos durante la inversión probabilística. Todo lo que le mostré anteriormente básicamente asumía que nuestras metodologías son isotrópicas, que pueden ser caracterizadas conociendo 3 parámetros elásticos, pero sabemos que el subsuelo generalmente no es así. Generalmente el subsuelo es más complejo, las rocas son más complejas. Rob acá mencionó hace un rato el efecto de anisotropía o el impacto que puede tener la anisotropía en la producción de imágenes sísmicas, y pero es una sorpresa, la anisotropía también puede tener un efecto en las amplitudes sísmicas, no solamente en los tiempos de llegada de los frentes de onda, sino también en las amplitudes que grabamos en la superficie. Y eso es algo, si se quiere, en lo que la industria de inversión ABO ha estado atrás, si se quiere, retrasada un poco, en comparación con la industria de procesamiento y de imaging, donde ha sido desde hace ya unos años bastante común incluir anisotropía en los algoritmos de migración. La única excepción es las técnicas de inversión azimutal. La inversión azimutal es estándar, parte del flujo de trabajo, pues considerar la presencia de anisotropía azimutal. Pero la anisotropía BTI, que si se quiere es la más común y es la que esperamos conseguir en casi todos los datos, si se quiere se ha dejado por fuera en los desarrollos de los algoritmos de inversión ABO. Simplemente para describir un poquito cuál es el problema en términos matemáticos, ¿okay? Esta ecuación es una ecuación que permite calcular los coeficientes de reflexión de onda P en base a diferencias o contrastes de impedancia acústica, contrastes de WPB, contrastes de densidad y, en este caso, contrastes en los valores de delta y epsilon, que son los parámetros de Thomson, que nos permiten describir rocas en función de su anisotropía. Y si ustedes miran esta ecuación, que es la ecuación de Ruger, es la aproximación de Ruger para medios PTI, si miran este término y este término, ambos dependen del seno cuadrado del ángulo. ¿Ok? Aquí está el contraste en delta, aquí está el contraste en PPBS. Y si este valor PPBS es 2, su inverso es 4, 1 sobre 4, resulta que esto termina cancelándose y luego la contribución del cambio en PPBS termina siendo casi igual que la contribución del cambio en delta. Entonces, el gradiente de la respuesta ABO, que es lo que generalmente se relaciona con los cambios de PPBS, resulta que puede estar afectado significativamente por cambios en delta. Y ese es el problema que nosotros hemos visto en muchas inversiones ABO, que cuando utilizamos una solución isotrópica, cualquier cambio en el gradiente se traduce en un cambio en PPBS, porque ese es el único parámetro en una inversión isotrópica que representa un cambio en PPBS. En una inversión anisotrópica podemos separar esos cambios en el gradiente en dos contribuciones. Un cambio a partir de los valores de PPBS y un cambio relacionado con los valores de delta. Entonces, esto nos va a permitir, por cierto, otra ventaja, que es que en vez de utilizar solo 3 parámetros para caracterizar la roca, ahora podemos utilizar 5 parámetros. ¿Okay? Entonces tenemos de nuevo 2 variables más que podemos utilizar para separar la fase. La clave es que necesitamos registros. Necesitamos registros de epsilon y delta para poder calcular los subvalores para cada una de las fases. Las compañías de servicio que hacen este tipo de logging y de adquisición de registros ya tienen bastante desarrollo en sus herramientas de sónico y estamos viendo cada vez más común operadores grabando datos de anisotropía o registros de anisotropía. Y eso es lo que nos permite a nosotros básicamente correr este tipo de inversión. Esto tiene implicaciones no solamente en la inversión probabilística, tiene implicaciones en la inversión determinística e incluso en pasos tan sencillos como la extracción de undícula. Esta es una extracción de undícula utilizando modelos isotrópicos. Fíjense que las undículas en algunos casos, estas son diferentes undículas para diferentes ángulos de incidencia. Y básicamente lo que siempre vemos es que los ángulos lejanos no coinciden con los ángulos cercanos cuando utilizamos modelos isotrópicos. Y entonces nosotros decimos, bueno, no, es que los ángulos lejanos tienen muy buena calidad, no vamos a utilizar esos ángulos, vamos a utilizar solo los ángulos donde nuestras undículas se ven chéveres. Pero resulta que si cambiamos el modelo y decimos, bueno, ¿sabes qué? Yo creo que estos datos más bien tienen efectos de anisotropía, y entonces ahora nuestras undículas, incluso para los ángulos lejanos, resulta que coinciden con las undículas, o están en mejor acuerdo con las undículas de los ángulos cercanos. Y si vemos los sismogramas sintéticos, ¿okay? Aquí tenemos 3 sismogramas sintéticos, este para ángulos de incidencia entre 5 y 10 grados, 20-25 grados, 35-40 grados, ¿okay? En el centro, los colores en el centro representan el sismograma sintético, y alrededor vemos una sección alrededor del pozo, son los datos reales, y este sería el amarre utilizando el modelo isotrópico. En los datos, por supuesto, en los ángulos cercanos, se ve perfecto, los ángulos medios también no se mal, los ángulos lejanos, bueno, no sé, algunos problemas. Estas amplitudes aquí parecen muy altas comparado con lo que vemos en la seismic. Pero cuando hicimos el amarre con los datos utilizando el modelo BTI, esto fue lo que obtuvimos. ¿Okay? Isotrópico, BTI, isotrópico, BTI. Entonces ahora resulta que nuestras amplitudes modeladas reproducen de manera mucho más cercana las amplitudes que vemos en los datos reales alrededor de la localización del depósito. ¿Y qué efecto tiene esto en los resultados de la inversión probabilística? Bueno, este es un dato de un pozo costa afuera, en la costa este de Canadá, bastante famoso, porque básicamente el pozo se perforó con estas expectativas. Verde, en este caso, significa arena con hidrocarburos, ¿okay? Y en este proyecto se había corrido una inversión, no era esta inversión, por supuesto, es una inversión determinística, y los resultados de la inversión lucían como lo que se ve en el track, aquí en el centro. ¿Okay? Este track a la derecha son los datos reales. Fíjense que los datos reales en realidad no consiguieron o no mostraron presencia significativa de arena con hidrocarburos. Pero la inversión inicial producía un resultado que predecía arena con hidrocarburos. Luego de, por supuesto, mirar el problema, mirar bien los datos, pues, BTI fue uno de los sospechosos, uno de los que le echaron la culpa del fracaso de este pozo. Y en efecto, se acercaron a nosotros, en este caso a Equinor, fue con quien hicimos este proyecto, y básicamente nos dijeron, mira, queremos hacer una inversión BTI en estos datos, porque nosotros pensamos que tuvimos este problema, que la razón de este problema fue la presencia de efectos BTI. Y en efecto, corrimos la inversión, asumiendo medio BTI, en vez de medio isotrópico, y en efecto la solución ahora coincide mejor con los datos observados. La solución BTI básicamente muestra que el pozo era seco. Lamentablemente, generalmente esto se produce, este tipo de corrida se produce después de que se encuentra un caso no exitoso que conduce pues, a repensar lo que se había hecho antes y probar nuevos algoritmos. Y esto básicamente es una comparación de nuevo de los resultados isotrópicos y de los resultados BTI y comparado con los registros. Y aquí las líneas rojas son los registros observados para impedancia acústica, VP esencial y epsilon y delta. En el caso de la inversión isotrópica, no hay las líneas negras en el background, las líneas negras en la parte de atrás son los modelos posibles, en realidad es la distribución de posibles valores de impedancia acústica, VP esencial considerados dentro de la inversión probabilística, y en la inversión propiamente probabilística, vemos que ahora estamos explorando no solamente cambios, estamos considerando no solamente cambios en impedancia acústica residencial, sino también cambios en epsilon y delta, y básicamente esos cambios en epsilon y delta lo que están haciendo es corregir los valores de BPBS que se habían explorado en la solución inicial. Entonces, lo que está sucediendo es que cuando incluimos epsilon y delta, por ejemplo, en este intervalo, los valores de BPBS resulta que no son tan bajos como la inversión isotrópica estaba prediciendo. Y básicamente, esos valores de BPBS son los que, junto con valores bajos de impedancia acústica, son los que se utilizan para identificar el fondo hidrocarburos. Ok, en conclusión, la inversión ABO probabilística permite un número, yo creo que infinito de interpretaciones o diferentes enfoques a la interpretación. Ya no solamente podemos utilizar inversión probabilística para filtrar superficies, para filtrar horizonte, podemos utilizar inversión probabilística para mapear las probabilidades de esa titología. Podemos entonces, como le mostré, obtener probabilidades para superficies y podemos construir modelos, podemos hacer modelos de escenarios P10, P50, P90. Algo clave en todo este proceso es el uso de información geológica adicional como los espesores de cada fase, el orden estratigráfico de cada fase. Eso es lo que nos permite en realidad tener mejor resolución que los métodos determinísticos. Y con este último ejemplo, lo que en realidad quería ilustrarles es que en este tipo de inversión probabilística es muy fácil incluir modelos físicos más complejos. No solamente BTI, es muy fácil extender esto para condiciones HTI e incluso incluir dentro de la inversión probabilística parametrizaciones utilizando mediciones provenientes de diferentes métodos geofísicos. Podemos invertir simultáneamente modelos sísmicos y datos electromagnéticos, por ejemplo. Eso es algo que es bastante sencillo de hacer en este framework, porque nos evitamos todo el problema de resolver el problema inverso de manera determinística, en el cual necesitaríamos una función objetivo y básicamente una matemática mucho más compleja y limitada de lo que permite el método probabilístico. Entonces, con eso, solo quiero agradecerles, ¿verdad?, por quedarse hasta esta hora de la noche. Si tienen alguna pregunta, con mucho gusto.
Ya metodológicamente hablando, cuando se sienta el intérprete con ustedes, por ejemplo, o se hace clave esa generación de curvas de probabilidad inicial de la caracterización geoestadística. Y uno como intérprete no necesariamente tiene la fundamentación en geoestadística, que es una ciencia relativamente compleja.
Sí.
Y entonces, si uno se equivoca en esa, digamos, parametrización inicial, en esas curvas de probabilidad inicial, el resultado puede ser que está bueno. ¿Cómo manejar ese tema de asegurarse de que lo que se carga el sistema está bien y que de ahí para adelante puedes confiar en los resultados?
Sí. Una de las cosas que yo creo que nos ha permitido tener buenos resultados con este tipo de proyectos ha sido esa colaboración bastante cercana con los intérpretes en el lado del operador, la experiencia nuestra mirando muchos de estos proyectos, y esa colaboración es la única manera de lograr que la información que se coloca en los modelos iniciales sea la mejor posible. En efecto, al igual que cuando diseñamos modelos de baja frecuencia para inversión determinística, que pueden básicamente terminar sesgando la respuesta a la inversión en un sentido u otro, en este caso también, definir esos modelos de probabilidad inicial de una manera errónea van a terminar también en predicciones erróneas. Yo diría que la única solución es colaboración, experiencia, contar con experiencia de los intérpretes que conocen el área, experiencia de los geólogos que conocen el área. Esto es un método, cuando nosotros lo hemos presentado, ha sido bastante atractivo para geólogos, no solamente para intérpretes sísmicos, generalmente físicos, sino también para geólogos, porque plantea el problema en términos un poquito más conocidos para los geólogos, ¿no? Entonces, es importante el input de los geólogos, de los geofísicos, incluso de los ingenieros de yacimiento en algunos casos, para tratar de formular el modelo más general que explique los datos que estamos tratando de invertir. Pero sí, no, o sea, requiere un trabajo en conjunto.
Raúl, la primera impresión que me da a mí, yo soy intérprete, cuando el método probabilístico que me pareció interesante, evita los dos pasos de calcular impedancia. La primera impresión que me da es que yo voy a perder como el control, ¿cierto? O sea, porque estoy evitando dos pasos que para mí son claves, para esa es la interpretación, que yo pueda controlar como esa parte de la mecánica de rojas, esa parte de generación. ¿Es como impresión mía o...?
No, sí, afortunadamente, cuando nosotros corremos este tipo de inversión, en paralelo se corre una inversión determinística también. Generalmente lo utilizamos como QC, ¿ok? Porque al final igual tenemos que condicionar los datos. Al final, igual tenemos que extraer ondículas. Entonces, no son dos flujos totalmente separados. Nosotros, particularmente en QI, nosotros probamos todo nuestro condicionamiento y toda nuestra extracción de ondículas con pruebas de inversión. Entonces, al final, siempre terminamos corriendo una inversión determinística para apoyar, si se quiere, lo que estamos teniendo en los datos de inversión probabilística. Pero sí, todavía en realidad necesitamos, para no perder ese valor extra que todavía nos puede dar la inversión probabilística, perdón, la inversión determinística, en realidad todavía no tenemos. No es si se quiere, no es el objetivo principal del proyecto, pero miramos a los resultados de inversión determinística para tener una guía de lo que va a suceder.
Pero esa es lo que justamente dice Iván. No solamente la sísmica, también es algo.
Sí,
Ahí queda un.
claro. No, yo creo que la diferencia es el uso que le estamos dando en este caso a la inversión determinística. O sea, nosotros sí proponemos igual la inversión determinística, pero nuestra solución de modelo de fase en realidad no está basada en la inversión determinística, está basada en la inversión probabilística. Pero los volúmenes de inversa acústica de presencia van a estar disponibles en caso de que el intérprete diga, no, bueno, yo quiero en realidad confirmar eso con información determinística.
Una pregunta, Raúl, en comparación, o sea, la inversión determinística, no sé si la conoces paralelo cuando tienes ya los modelos P90, P50, ¿has comparado esa determinística? ¿Cuál se aproxima más?
Sí, y de hecho no hice mucho énfasis, pero básicamente aquí está. Este es, por ejemplo, el mapa de, en este caso, el espesor de arenanita, que habíamos calculado con la inversión determinística, y estos son los modelos, el mapa de espesor de arenanita para el modelo P10, P50 y P90, y básicamente la inversión determinística se aproxima bastante al P50. Básicamente la solución promedio.
¿Lo has visto eso en varios de los casos que han trabajado?
Sí, generalmente la inversión determinística siempre se aproxima bastante cercana al modelo promedio.
¿Por qué no usan el PMI?
¿Tení?
Es más alto que el P7.
Ok.
Porque si usan el PMI se parece más al PMI.
Ok. Sí. No sé, creo que ninguno de los clientes nos ha pedido mirar el PMI. Siempre hemos ido con el estándar PMI P50-90, pero lo bueno es que teniendo la distribución de probabilidades a partir de la inversión, cualquier P que tú quieras se puede calcular.
¿Hay más preguntas? ¿No? Muchas gracias, Raúl.
Gracias.